Welcome to educator.com, and we have another instance for learning Introduction to C++. Today, we're handling structures. Okay, we use structures to keep related data together. You may have noticed from a previous homework assignment that you'd have more than one array, and so you want to get the name array, and then you get to get the sales array, and various things like that. And each one has got indexes. You get to make sure your indexes stay lined up with each other. With a structure, we can put all of that into one structure. So the syntax uses the keyword struct. We're going to cover some examples. How to access members of a structure. Once you get it into the structure, how do you get the data out? We can have structures that contain other structures. We want to get to those members. How do we initialize the structures? We get an array of structures, multi-dimensional arrays of structures, pointers to structures, allocating, deallocating them. We get the memory from heap, put it in the structure. When we're done with it, put it back. And accessing members of the pointed to structure. Okay, we need to keep our data organized. The computer doesn't care where you put the data, but as humans, we need things organized. We need things to be in certain places, and it's also a little bit easier. You don't have to deal with, okay, I want name of 0, I want age of 0, I want score of 0. You just put all that into a structure, call it person or whatever. Then you have person of 0, and you get that person's age, you get that person's name. So we can keep our collections of structures versus multiple arrays of data. The multiple arrays are also troublesome when you want to keep your data in various collections, such as arrays, stacks, sets, binary trees. You have a binary tree. Binary trees, by the way, are used a lot for searching. It's like a dictionary type of thing where you want to say, well, the letter, it starts with A, so we know it's towards the beginning of the dictionary when we start looking for something. So we have, here's a few here. Here's an array of IDs. We have 100 IDs. We have 100 scores. We have 100 handicaps. Well, how do you put these three into a stack or into a set? You have to have 3 collections, 3 arrays, 3 stacks, 3 binary trees, what have you. But if we have a player, which consists of the ID, the score, and the handicap, it's much simpler to deal with that. So now we can put this player into this binary tree or into this array. And this kind of leads us up to object-oriented programming, which will be covered later. But you could consider this as a object. So here's our general declaration. Here's our general syntax for declaring a structure. We have a struct keyword. And I've got square brackets here in italics, because you don't have to give it a structure name. You should, but you don't have to. If you don't, it's considered an anonymous struct. And then we have the type of the member and the name of the member. As many of these as you need, and then you end your curly brace. And then you can give each object, you can add those onto there. And again, these are optional. You don't have to do that. So here's an example. We have a person, struct person. He has a name, which is a string. He has a height, he has a weight, and he's got a score for whatever game the player is for. And we've got 3 players declared right here, P1, P2, and P3. Now, the structures can be declared without declaring the object elements. That way you can use it as a type. You can use it as a type anyway, but it's better to just leave it out and then declare them. So we can have, when you do that, you do need the semicolon, because you need the semicolon to separate your declaration section of your code from your execution part of your code. So here we have a parent structure, the name, age, and a gender. And now we can use parent like a type. Instead of being integer or double or char or what have you, we can say parent. And we have a variable mom, who is a parent. And initialize it. There's mom's name, Gracie. Mom's age, or at least what she tells us her age is. And her gender is female. And then dad, whose name is George. I don't believe his age either. And is male. So now we've got 2 variables that in memory somewhere, we've got mom, who has a string with whatever her name is, a float for her age, and a char for her gender. This chunk of memory has been allocated for mom, and a similar chunk of memory has been allocated for dad. Now, we're going to use some of these structures. We're going to have this example for a person who has a name, an age, and a height. So we'll have Abel. Again, don't forget that semicolon. We have Abel, who is declared to be his age is 27. He's 175.5 centimeters, feet, what have you. Feet, that's pretty tall. Barbie, who is 57, oh yes, Barbie doll is 57, that's true. But she's only 12 inches is how high Barbie is. Well, this is a different Barbie. And then we have anonymous. And we did not initialize anonymous for whatever reason. But we can assign, see, these assignments were done at compile time. This assignment is at runtime. We set anonymous equal to NA00.0. Like I said, make sure you put these zeros in there so that you know what the values are. And we can use it now, when we declare it as a type, this is a variable. We can use it like any other variables, including Abel is being assigned to Able Jr. So we have a person called Able Jr., and all the members of Able will be copied to all the members of Able Jr. So it's very powerful syntax here. You can do many things in here. So you've got your memory chunk. We've got Able is here. We've got his name uses up so much space. His age is here, and his height is here. This is this little section that belongs to Able. There's all sorts of other memory out here, and there's a chunk that's Able Jr. So we do this copy. We'll copy that to that, this to that, and that to that. Now, we've got the data. Now we've got the data initialized. How do we use it and get the members, to get the data back and forth between the members inside the structure? So we use the period, for the most part, to access a variable's member. So we have a company that has a name and a city and float their annual sales. We'll initialize C1, company 1, who's in Boston, and got very little sales this year. Let's fix that. C1 dot sales is now, so we've got this number, floating point number, is stored in this member. And we can use that in an expression, just like any other expression. So let's grab the sales from this company, multiplied by 0.15, and that's the taxes that the company owes based on this tax rate, which of course should be a variable because it changes every year. And we have, since it's a structure, defines a new type, you can have a structure that contains structures. Here's a nice example. Here's a structure, a tire. We're simulating a race car. You have to know about the tires and the pressures. So we've got the current temperature and the current air pressure of this tire. Now, the race car has got a string as its designator. And then we have person structure from earlier, who is the driver of this race car. The float would keep his current speed, the weight of the car, and the horsepower of the car. And then we've got tires, the front left, front right, rear left, rear right, and the spare, which you shouldn't have a spare. It's a race car. Race cars do not carry spares. They stop at the pit, and all the tires get yanked out. Brand new tires get put on. But you would need this for a simulation of an automobile, because the faster the car is going, the more the tires will heat up. If it makes a lot of left turns, the temperature of the left tires may be different than the temperatures of the right tires. So we've got a tire type, which is a structure defined up here. And of course, you could have all sorts of other variables. You might have the dimensions, it's 15, int radius, maybe it's a 15-inch tire, what have you. So whatever data is required for this simulation of race cars, you've got the tire, and that structure is included in a larger structure. And well, now we've got another problem. How do we initialize this structure of structures of structures? Well, our old friend the curly brace comes back to the rescue. So here we have a person with a name and age, a company with a name and city, a race car with a designator. The driver is a person. He's got a weight, a horsepower, and the owner of this race car is a company. So here's how we initialize it. We have the curly brace for the entire race car. Your first set of curly braces inside here is your person, whose name is Mario and his age is 26. And then outside of the curly braces, we've got our weight, we've got our horsepower, and then more curly braces, because the owner of this car is General Automotive, who operates out of New York. Now we need to access the data within the data. So we defined car 42. Car 42 dot owner gives you this data. Dot city gives you that data, which we're changing to Chicago, because it turns out we got the wrong city. Now, a little more valuable things is to take a structure, take an item, a collection of related data to some object, and put it into a larger collection. And our first collection is an array. We have an array of structures. Now, one of the things I wanted to mention here is, again, the compiler looks at all these types. It calculates exactly how much memory is going to be needed for each one. So here we have a stock ticker, which consists of a string for the New York Stock Exchange ticker. Its full name is Oracle, and this is Oracle. Today's low is 32, and it would be awfully miraculous if today's low actually was 32.5. And 38.9 is the high, and the volume was 12,459 shares traded hands. And IBM is the second stock ticker. You see, we've got our first curly brace is for the entire array. Then the internal curly brace is for our first structure. And then another internal curly brace for the second structure in that array. So we can say, well, this is a stock ticker called ST. We don't know how many there are. We'll let the compiler count them. ST1 volume is going to add 300 to it. So we go to 1. Remember, it's not the first, it's the second. So that's over here, this is IBM. And we want the volume, which is this number, and we want to add 300 to it. And we want to print out the sticker, which would print out IBM. And of course, we can have multi-dimensional arrays. Now remember, the more of these you put in there, the more memory it takes. The more you put into these, they get multiplied by each other. So this is, here we have a wonderful little weather node. We want to simulate the weather. We want to predict the weather. We divide, in this particular example, the county into a large grid. The grid happens to be 2,000 by 2,000. We don't know how, in the node area is how much space is a given grid, a specific node, how much area is in that node. And so for each one of these nodes, we need the air temperature, the ground temperature, the moisture content, the wind direction, and the wind speed. Now, given that information, we can say, well, we've got a wind coming in from this direction, which affects all of these nodes, and then all of these nodes affect all of these nodes. If there's a section here where these nodes have got a higher ground temperature, that will affect the air temperature, that will affect the wind speed. So as we come through here and make all these calculations, we've got this nice large grid full of nodes. Each node has got all the information we need. We can make our calculations and maybe make some type of prediction to say if the wind comes in from this direction at this speed, it will come out this way at that speed, or it will get rain, or whatever else will happen. But like I said, notice this is 80 million bytes because we've got a float here. That's 4 bytes. Another 4, another 4, another 4, another 4, multiplied by 2,000, multiplied by 2,000. And at this particular latitude and longitude, we want to set the air temperature to 21.3 Celsius. And this is why weather is difficult to predict. This is literally the types of things they have to do. This is why they have parallel computations working on it. They've got huge supercomputers where they've got millions of nodes, and with much more data per node and massive amounts of calculation. And they still can't get the weather right. Now we have pointers to structures. It's like any other type of a pointer. We declare it with the asterisk that says this is a pointer to a person, and we have the new operator to get a new one. So the program will go out to heap, grab enough memory to fit one person, and then this pointer is now pointing to where that memory is. And this is the only way we can get self-referencing structure. So here we have a person with a mom and a dad. Well, you can't just put another person inside of a person. The compiler won't let you do that. But you can have a pointer to a person. And then at one time, you can go allocate some memory and set mom equal to whatever the data is, set dad equal to whatever the data is. And one thing I want to also stress here is, remember here, person is a structure. The amount of space depends on the amount of space of each of its members. So if we had a car, for example, with a driver, let's say that's a string, and a float for the weight, another float for the horsepower, and whatever else you want to put in there, and that's all part of the car structure. All of that will be put together in continuous memory, and the compiler knows how large this is. So if you have an array of these, let's say you had car, let's say it's like that. Let's actually make it 100. So the compiler will take the size of this car structure, multiply by 100, and allocate enough memory to handle everything. Now, I told you it's safer to do pointer arithmetic inside memory. You don't have to worry how large this is. If you have a pointer, let's say we have car CP, and we point it into C, that now points to the beginning, the very first structure for car. Now, if you add 1 to this, just 1, is that 1 byte? Is it 1 integer? No, it's 1 structure. Whatever this type is, however much space this requires, the compiler knows that when you take a pointer of that type, add 1 to it, add 2 to it, what have you, it goes to the next structure. That structure size is the unit of measurement for going to the next, pointing to the next structure in memory. It's something very important to remember. You don't have to worry about the size. The compiler worries about the size. Now, there's a way of accessing. We're talking about accessing a member. If you have, like we had that car, and it had a driver, so C.driver accesses that member. But if you have a pointer, then you have to dereference the pointer first, and then get the member. Well, we've got a shortcut for that. So here we have a person pointing, gets a new person, dereference that pointer, get that name, set it to Peter. Our shortcut is to use this operator, this dash greater than, or arrow, or whatever you want to call it. The pointer points to a member. So instead of doing this to get the name of Peter, we use this. And This is the same as this, but this is a lot easier. You will see this a lot because you'll see a lot of pointers to structures in code. You'll use that quite a bit, and so you'll see a lot of this particular operator to get to the member of a given structure. So it's less confusing in general, especially if you have a pointer to a structure, to a pointer to a structure, to a pointer to a structure, et cetera, et cetera. Here's a great example. We've got an employee structure, and he's got a name and a wage. You'd have a whole lot more than a start date, whatever. But we're only going to look at these two. The structure company has got a name, the city. We have a pointer to the boss employee, and we have an array of employees. So this is a special employee. That's the boss. So we'll have company, pointer. C2 gets a new company. We want to dereference that to get the boss and get a new employee, which now gets placed there. Now we want to set that employee's name. We want to set the boss's name. So we dereference the company, get the boss, dereference that, get his name, and then set it to what it is. You see, the more you nest it, the more confusing this can get. So the shortcut here, you take C2, pointing to boss, pointing to name, set that equal to Peter. Much simpler this way. And here we have a structure for pointers. It keeps all the puppies in one place. I like this one. He's cute. So anyway, thank you for viewing another lesson on Introduction to C++ from educator.com. I'll see you next time.